So in today's class, we will discuss about different computational models available in embedded system. So starting with the first one, that is data flow diagram, or we call DFG model. Okay, data flow diagram model, or data flow graph, or data flow diagram model. Okay, so as the name itself indicates, before starting with the concept, what is this modeling? Why model is required? In the last class, we have seen uh, issues related to the model. There are different types of model we need to represent it. Model in the sense, say you basically a user will give their requirement, right? If I consider the same example, like say smart room temperature measurement system, where you are supposed to maintain a room temperature at say 24 degrees Celsius continuously. So what we do basically is user will give their requirement. They will tell their requirement like I want the room temperature to be maintained for 24 degrees Celsius, not more than 24, not less. This is a requirement given. So for this requirement, we are supposed to design. So the first step in designing the requirement is nothing but developing a model for that requirement. Okay, whatever specification the user give or whatever requirement the user give, it has to be modeled, right? It has to be modeled in the sense it has to be represented in the form of certain models. So in that, the first type is data flow model. Data flow, as the name itself indicates, it gives us the information, like overall information starting from the first input and how it moves to the output, right? It translates the data processing requirements into a data flow graph, right? As well as a data-driven model in which the program execution is determined by the data. How exactly this execution is determined, all that will be represented in the form of a model. It emphasizes on the data and operations on the data, which transfers the input to the output, right? It just gives the information how exactly this input as well as the output transformations will be done. All that information will be given through visual model. That's all. Okay, visually you're going to represent it, right? Visual model involves operation on the data, that is nothing but a process, is represented using a block or a circle. Okay, one process is represented using a block or a circle, and the data flow is represented using the arrow. To that circle, what is the input, what will be the output, that will be represented. The data for that particular process will be represented through an arrow. Okay, say for example, if I consider the next slide, say in this case, if you consider the circle is nothing but a process. Okay, and the data for this process is, say here A is the input, B is the input, and X is nothing but the output. That is nothing but data flow as well as data out, right? So if I consider the same example of monitoring the room temperature, what is the input? Say process is monitoring, right? Process is nothing but checking the room temperature. So in order to check the room temperature, we have to give some input. Right? What is that input? Input is nothing but reading the temperature. So that is the input. It will be represented through an arrow and given to the circle. Circle is nothing but what? A process. There, the process can be, say, three different types of process. Maybe they're like temperature is equal to the threshold, temperature greater than threshold, temperature less than threshold. And for that, what is the output, right? That is also represented by a data flow. So in general, it gives us the visual model. Say for example, one example is given. This is a requirement. Requirement is like say x is equal to a plus b and y is equal to say x minus c. Okay. So here plus as well as subtraction minus. It is nothing but a process. So first I'll have plus. Input for this addition is a and b. So these are the data for that. It will be given to the process after addition, after adding, after the process is complete, and output will be generated. It is nothing but again a data flow, which is nothing but x. Okay, next process is subtraction. You can observe here x minus c is nothing but the data for that process, for that subtraction, and the output of that is nothing but 5. So this is nothing but data flow. We call this as data flow node. So basically data path, okay, data flow path from the input to the output is, this is nothing but a path. How exactly the input move towards the output after a process is nothing but a flow path. So in general, DFG, data flow graph or data flow diagram, is said to be acyclic, okay, if it doesn't contain multiple values for the input variable and multiple output values set of inputs. Okay, feedback input or even are the example for non-cyclic inputs. Here, in this particular data flow graph, in a simple data flow graph, we don't have like a feedback given to a node, or else we cannot have representations like, say, some representation may require conditional check. Okay, some conditions we need to verify. Based on that, you're supposed to take an action. All that cannot be mentioned here. Just a process will be mentioned. So in order to overcome that, one more, so this is the first simple modeling, data flow graph modeling, representing any process using a node, using a process, as well as the data inputs and the output. Okay, and second type of modeling. Okay, the second type of modeling is computational models. That is nothing but control data flow graph. Okay, control data flow graph or control data flow diagram model. It is a continuation of the previous model, data flow graph. Along with that, say the name itself indicates control data flow. What is this control data flow in the sense? It is nothing but it translates the data processing requirement into the data flow. The same procedure. Okay, whatever requirements you have, it will be translated to the data flow. For the visual representation, it will be translated. Okay, model application in this particular models, it involves conditional program execution. Also, in the previous modeling, in data flow modeling, we didn't have the option to give the conditional codes. Here, some conditional codes will also be given. Okay, so which contains both data operation as well as control operations using data flow graph as the element and conditional constructs as the decision makers. Okay, we'll consider one example and we'll check it. So this particular model contains both data flow nodes as well as decision nodes. Okay, remember that in the previous model we had only data flow model, how exactly the data will be moving from one point to the other point. Whereas in this particular conditional control data flow section, you have both, that is nothing but data flow model as well as decision model. Okay, decision nodes. Okay. So here the control node, okay, then the remain that is what is that data flow will be represented using circle itself. Okay, uh, that is the process will be represented using a circle and the data flow using an arrow. It is the same procedure. Whereas here for the control node is represented by a diamond block. Okay, diamond block represents the control. The conditional check will be represented. Based on that, certain actions we are supposed to take. It is nothing but a decision making element. Okay, translates the requirement which is modeled to a concurrent process model. Okay. So ultimately that control node or that decision making will decide what is the action to be taken if the condition is true or if the condition is false. What is action to be taken, that also can be represented using this control data flow graph. Okay, so if we go through the block diagram, we can check here. See, this is an example. Here some condition is here. Say if flag is 1, then you have to perform x is equal to a minus b, a plus b, sorry, else y is equal to a minus b, certain condition. Okay, so here this is nothing but this is how you represent a condition using a diamond block. Okay, in the diamond, the input for this, some input should be given to this. That is nothing but flag should be red. So if flag is equal to 1, a question mark indicates you're checking flag is equal to 2 condition. Either it can be true or false. If it is true, then the process to be done is x is equal to a plus b. Okay, you can observe here. If it is true, then process, that is addition process, will be activated. For that, the data flow inputs are a as well as b, which is represented through an arrow. Okay, and the output is nothing but x will be given to the output section. If it is false, then the process to be selected as subtraction. Inputs are same, that is a as well as b, and which will be given to the output. That is the continuation of the data flow, control data flow, where you can represent the conditional check also. Okay, same example, if I consider monitoring the room temperature, there we have 3 different conditions, right? Whether temperature is equal. If temperature is equal, first condition, so the first process will be reader temperature. Okay, say temperature x is read. Once it is read, next you have to check the condition, whether if or whatever, if x temperature is equal to, say, my threshold, then what? No action is required, directly though. If x is greater than threshold, what is the action? Like reduce the temperature of AC. If x is temperature is less than threshold, then increase the AC. So these are the three different actions, right? So it can be put in the conditional check, and then there is nothing but through the control node we can verify whether it satisfies or not. If it satisfies, certain action; if not, some other action will be taken. Okay. This is the second type of modeling, that is control data flow modeling. Next, the third type of modeling available is state machine model. Okay, state machine model, it is based on the states and state transition. It represents like the process will have different states, right? Like execution state, or say sleeping state, or waiting state, or the processing running state. Different states will be there. So this model will be represented using the states as well as state transition. What is state transition? State transition is nothing but movement of one state, that is a waiting state, to the running state. In order to move from waiting state to the running state, there should be some input given, or there should be some resources given for that particular system. So that is nothing but state transition. So this describes the system behavior, and this system behavior with states as well as some events, and when that event occur, what is the action, as well as transitions. Okay, so these are the four major concepts which we need to look into in case of state machine model, that is states, event, actions, and transition. Okay, so state is nothing but a representation of a current situation. So a new event, an event in an input is an input, right? State is the present status of that particular process. For that, some input will be given, and that input we call it as an event. Okay, event to that state. The event acts as a stimuli for the state transition. Based on that input received, there may be a state transition from one state to the other state. Okay, that is because of the input, the state transition will occur. And transition is a movement from one state to the other state, right? What is action? Action is nothing but an activity to be performed by the state machine. When there is a movement, say from waiting state to the running state, when there is a movement, in running state, what is action to be performed? That has to be programmed. Or in waiting state, what is action to be performed? Waiting state may be like waiting for the resources. So we have to wait. Once we get the resource, that is nothing but once that input is given, there will be a transition from the waiting state to the running state. When it enters the running state, what is the next process to be done? What is the next action to be taken? Say for example, same example, if I consider room temperature, now the reading the temperature is done. Now you have read the temperature and processing is done. When processing is done, that is when running is done, what is the next step? Next step is like controlling the AC, controlling either increasing the AC temperature or reducing the AC temperature. That is nothing but the action, right? A finite, and the next concept, a finite FSM. I think you might have heard this FSM. That is nothing but finite state machine model. It is one in which the number of states are finite. Okay, we can exactly know how many states are there, so we call it as finite state machine. In other words, the system is described using a finite number of possible states. Most of the time, state machine model translates the requirement into the sequence driven program, right? Basically what requirement user give, that requirements can be represented using this FSMs based on the sequence of that operation. Okay, hierarchical or concurrent finite machine model is an extension of FSM. There is one more concept, that is hierarchical or concurrent FSM. Okay, we'll discuss that one by one. Say if we consider one example, automatic uh, seat warning in an automatic in a car. Okay, seat belt warning system. If you consider now, what I'm suppose say that user uses the requirement. User says that I want to develop a system, that is seat belt warning system. Okay, so the requirement as per the user is when the vehicle ignition is turned on, you turn on the ignition. When we turn on the ignition, and the next condition is, and the seat belt is not fastened within 10 seconds of ignition. You will turn on the ignition. After the ignition is on, within 10 seconds, you are supposed to put the seat belt. Okay, and now if you don't put a seat belt within 10 seconds, then in that case, and when ignition is on, in that case, what you're supposed to do, the system should generate an alarm signal for 5 seconds. This is the requirement. You turn on the ignition, within 10 seconds of the ignition turned on, you're supposed to fasten the seat belt. If the seat belt is not fastened within 10 seconds, an alarm should be generated, and that alarm should be on for 5 seconds. Okay, what is the condition to turn on the LRAM? Ignition key is on and it is on for 10 seconds. Until 10 seconds there is no seatbelt fastened. Okay, and the next step, next requirement, the LRAM is turned off. Now the next condition arises, whether how to turn off an LRAM. The LRAM is turned off. Next step is you need to turn off. So for that purpose, LRAM is turned off. Okay, when the LRAM time expires, say for example, we will keep the LRAM time as 5 seconds. Okay, LRAM should be on for 5 seconds. If the time expires, you're supposed to turn off the LRAM. That is first condition. Or suppose say that the passenger fastens the seat belt. Okay, if he fastens the seat belt, in that case also LRAM should be turned off. Or one more condition, if the ignition is turned off, right? If the ignition also turns off, then car is in off state. Then in that case, you have to turn off the LRAM. So these are the three conditions to turn off the LRAM. One is LRAM time elapses. Second one is second one is if suppose user fastens the seat belt, and third one is if the ignition is off. So this is the requirement what the user will give you. For this requirement, we are supposed to develop a system. So before developing a system, what we have to do is we have to develop a model. Okay, now developing a model, you can represent the same model for this particular requirement. You can represent it using your data flow graph, right? You can represent it using your conditional data flow graph. It is control data flow graph. And one more model what we have discussed is discussing here is finite state machine model. We can represent the requirement using FSM also. So we will discuss this in FSM. You can observe here in first initially say the first state LRAM is I'm basically deciding the state of the LRAM, right? LRAM initially the first state is LRAM is off. Okay, LRAM off state. Now what is the input for this? When you ignite a key, right, and the ignition is on. Now when the ignition is on, what happens? The state, there will be a transition of a state. This wait, it goes to the process goes to the waiting state. Waiting for what? Waiting for, say, fasten the seat belt. Okay, you will turn on the ignition. Just imagine the concept. Initially LRAM is off. Now you'll enter a vehicle and turn on the ignition. When you turn on the ignition, there is a transition of state from LRAM off to the waiting state. That is, waiting state in the sense the system will wait for the user to fasten the seat belt. If immediately the user fastens the seat belt, you can observe here, if seat belt is on, from waiting directly the LRAM will be lost. Correct? Again, there will be a transition from waiting state, it goes to the LRAM off state. Or one more condition, one more event may occur. Suppose if again the user turns off the ignition. Okay, if the ignition key is off, again there will be a transition from waiting state to the LRAM off state. That is same. Now suppose if this process, this event doesn't occur, if key is not on, off, or if seat belt is not fastened. So what is the next step? Ignition key is on now, seat belt is not fastened. It will wait as per the requirement. We need to wait for 10 seconds, right? So system will be waiting for 10 seconds. Okay, it waits for 10 seconds. Okay, you can observe here. After 10 seconds, the timer will expire, right? And it will turn on the LRAM. LRAM will go to the on state. Now LRAM is in the on state, right? After 10 seconds, when the ignition key is on, there will be a transition from waiting to on state. Now here, next step is to turn off the LRAM. So as we have seen in the requirement, in order to turn off the LRAM, there are three different conditions. Either LRAM timer has expired, because as the requirement given, LRAM should be on for 5 seconds. Okay, so if it expires, you are supposed to turn off the LRAM. First condition. Second condition, if the seat belt is fastened, you have to turn off the LRAM. Third condition is if the ignition key is off, you have to turn off the LRAM. So here three events like LRAM time expired, seat belt is on, or ignition key is on. If any three event occurs, LRAM will go to the off. This is how you represent a requirement into FSM model. It gives the visualization for the designer how exactly the designing should be done. That is the first step. This is the third type of model, that is FSM model, finite state machine model. Okay. The next model, the fourth model, it is nothing but the sequential program model. Okay. In the sequential program model, the functions or processing requirements are executed in sequence. Okay, that is nothing but step by step this processing is executed or requirement are executed. The program instructions are iterated and executed conditionally, and the data gets transferred through a series of operations. So FSMs are the good choice for the sequential programming model. Okay, the flowchart is another important FSM already we have discussed. It is one of the good choice for the sequential programming model. And one more model in order to represent the sequential programming model is nothing but flowchart. Okay, flowchart is another important tool used for modeling the sequential program. The FSM approach represents the state, events, transition, and actions, whereas flowchart model the execution flow. Flowchart will give us exactly the flow of execution starting from initialization till the end. So we'll just go through the same requirement. I will represent the we will represent the same requirement of seatbelt warning system using flowchart. Okay, so the same requirement here when the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds of ignition, the system generates an alarm signal for 5 seconds. Okay, and second one, the alarm is turned off when the alarm time expires, or if the driver or passenger fastens the seat belts, or if the ignition switch is turned off, whichever happens first. Okay, so these are the requirements. Now using this requirement, we will plot a flow chart. So this is a flow chart. What is the first step? Turn on the ignition, right? You can just imagine the concept of car. You just when you get into the car, you will turn on the ignition. This is the first event. Okay, ignition is start. Ignition key on. Next step is once the key is turned on for the alarm, we are designing an alarm system. So the key is turned on as per the requirement. We have to wait for 10 seconds. For what? To fasten the seatbelt. So wait for 10 seconds. After 10 seconds, you are supposed to check. Okay, what you're supposed to check? Check whether the ignition is on. If ignition is on, fine. If ignition is off, what? Just stop the process, right? If the ignition is on, if it is false, you can say ignition is on, no, then end. If yes, now ignition is on, 10 seconds has elapsed, check the seat belt, whether seat belt is on. If yes, fine, end the program, right? If no, now the seat belt is not on, then what you're supposed to do, you're supposed to set the timer for 5 seconds and start the alarm, right? So set the timer for 5 seconds and start the alarm. Now alarm will turn on. It means that alarm will be on, it should be on for 5 seconds, or there are three conditions. It should be on for 5 seconds, whether timer has elapsed, or if the ignition key is off, or if seat belt is fastened, you have to turn off the alarm. So the next step is check whether ignition is on. If no, expire the time. Sorry, if no, then go to end. If yes, check whether seat belt is on. Okay, this is for the alarm turning off condition. Check whether seat belt is on. If it is yes, then stop the alarm and then go to end. If seat belt is not on, the next step is check whether the timer has expired. That is, you have to check whether it has alarm has been set for 5 seconds, whether the timer has been expired. If yes, stop the alarm, then end. If no, again this process should be monitored continuously. These three processes should be monitored, like ignition is on, seat belt on, timer expired on, right? Continuously they will be monitoring, and based on that the condition will take place, right? Is that clear? This is a flowchart representation of sequential programming. Okay, so this is a simple program of the previous example. Based on the flow chart, they're supposed to program. So we can just check it out. They define on 1, in the sense on is equal to 1. Similarly, define off is nothing but 0. Define s in the sense is also 1, true condition. Define no is nothing but 0. This is the program for the seatbelt system itself. Next, avoid seatbelt warning. First step is wait for 10 seconds. Wait for 10 seconds to fasten the seatbelt. Check at that particular interval, after that particular delay of 10 seconds, check whether ignition key is on. If this is on, then check whether seatbelt is on, or in the sense seatbelt is off. If seatbelt is off, then we are supposed to, if it is on, we have to come out. If it is off, then we have to set the timer. set the timer, that is on the set the timer for 5 seconds, on the LRAM, start the LRAM, right? Your LRAM will turn on. Then after that, once the LRAM is turned on, you're supposed to check that LRAM continues. There are three conditions to keep the LRAM off or to turn off the condition. That is, say, if seat belt is off, okay, if seat belt is off, and if ignition is off, and if timer expires, that is in no. Timer expires no in this, no in the sense all these are zero. If all these are zero, that is nothing but seat belt is zero and ignition is not off, okay, and a timer has not expired, then we have to wait in this loop. See here you can observe a semicolon is given at the while loop. It means that continuously it will wait in this loop. So in this, if any of the condition is satisfied, then we can come out of the loop and stop the LRAM. This is nothing but the simple code for that flow chart what we have given, right? A simple sequential programming model. So these are the different models available for the programming, and the last model available is nothing but concurrent uh, communicating process model, right? That is concurrent communicating process model is nothing but models concurrently executing the task process. The program instructions are iterated and executed conditionally, and data gets transferred through a series of operations. Here, the entire program, okay, it will be iterated, it will be divided into various functions and then executed conditionally. Certain processing requirements are easier to model in concurrent processing model than the conventional sequential execution, right? Why? Because I'll explain that sequential execution leads to a single sequential execution of it. What do you mean by concurrent model? First of all, concurrent in the sense, I'll have, say, previous example, if I consider, like there we had three different conditions to be checked. Whether ignition, in order to stop the timer, we have to check whether the timer has expired, or we have to check whether ignition key is off, and also we have to check whether seat belt is fastened, right? Is it possible to do it concurrently? Monitoring of all these three action can be done. In the previous case, it was like step by step. Is it correct? Was it right? First, you check whether the timer has expired, and also you check whether the seat belt has fastened. It was step by step. But if we have it concurrently, it will be better. So, so basically, sequential execution leads to a single sequential execution of a task, thereby leads to a poor processor utilization. Okay, if the task is split into multiple subtasks, it is possible to tackle the CPU usage effectively when the subtask under execution goes to await or the sleep mode by switching the task execution. Concurrent processing model requires additional overheads in the task scheduling, task synchronization, and communication. We will consider the same example so that it will be easier for you. Before that, I will just say some problem in this particular previous sequential execution. In the sequential execution, if I consider this section of the program, that is LRAM has turned on, just imagine the condition, LRAM has turned on, okay, ignition. Now in order to turn off the LRAM, what we are doing is we are checking whether ignition key is on. If on, yes, then go check seat belt is on. If on, then you are supposed to end the program, stop the LRAM. If not, seat belt is not on, then you have to check whether timer has expired. If yes, then you are going to stop. If no, you come back here. So this is step by step. First on, check the ignition key, next check the seat belt, next check the time expired. Now suppose say that now you are the processor is executing this particular state, ignition. It is checking whether the ignition is on, and during this process your timer has expired. Your LRAM will not turn off immediately because it should complete the execution of ignition, check the execution of ignition key on, then you should check the seat belt on condition, and then it will come here, right? Even though the timer has been expired initially at this particular juncture itself, it will not directly come here, since this process, whatever we have coded, it is step by step process. It will continue the first step execution, next the second step seatbelt, and next this one. So obviously there will be some delay. So we need, in order to avoid this, what we can go do is we can go for the concurrent programming model. So in this concurrent programming model, a separate task will be created, right? Create and init different events will be created, like say an event for wait, timer expire, ignition on, ignition off, seat belt on, seat belt off, LRAM timer start, LRAM timer expire. These are the different events, right? First event for say wait timer, timer should be on for 10 seconds, right? That is the timer expire. Next event is ignition on. Next event ignition off. Next is with respect to seat belt on, seat belt off. Next is with respect to LRAM timer on, start, as well as LRAM timer expire. So these are the events for, and also we have different tasks. We can consider this as function task like wait for the timeout, right? Create a task for ignition key status monitor. This is to monitor the status of the ignition key, as well as one more task to monitor the seat belt status, whether it is on or off. One more task to control the LRAM, to turn on the LRAM or to turn off the LRAM, and one more task to control, check the LRAM timer, right? So these are the different tasks for these applications, and so accordingly those tasks will be programmed concurrently. You can observe here, see, three different blocks are there. The three blocks in the sense, this is at one instant. This block one is wait timer task and ignition key status. This can be executed in sequence, right? This set can be executed first. Next is this one. Next this setup. Next is this setup, right? And whatever sets we have in to that, it can be executed concurrently. Say for example, wait timer task. Okay, here we have to wait for sleep, say 10 seconds. Set the set event wait timer expire. Okay, at the same time you can execute this task also concurrently. This can be executed. Ignition key status monitor. When it is waiting for 10 seconds, the processor doesn't have any other task, right? So what it can be do is ignition key status monitor task can be executed. That is continuously. At the same time it can monitor the status of the ignition key, whether it is on or off. If it is off, directly you can end the program, right? While one, if ignition key is on, set the ignition key on, reset event ignition off. Else, set ignition is off, reset event ignition is on. That is nothing but, suppose the ignition key, here you are going to monitor the status. Status is the event is check whether it is on or off. If ignition key is on, then what is the event you are supposed to take? If the ignition is on, then you have to reset the ignition event, reset the event ignition is off, right? We need to reset that event because ignition is on. Similarly, set event ignition off. Suppose say if the ignition is off, okay, if suppose if the ignition key is off, then what we have to set the event ignition is off and reset the event ignition on. So that is nothing but the task in order to monitor the ignition key whether it is on or off. Okay, so after 10 seconds, we can come out of this. These two functions or the task can be stopped, execution can be stopped and come to the next section. In this, you can check two other tasks like LRAM control task as well as ignition seatbelt status monitor. Okay, here LRAM control in the sense turning on the LRAM of LRAM, that is nothing but LRAM control task, and at the same time you can monitor the status of the seatbelt also. Okay, so this is nothing but a concurrent process. Here, wait for the signal, wait for the timer expire. Now here we'll get the input from here, right? You can observe here the input will be given to this. Similarly, the output of this, that is ignition key status monitor, will be given to both LRAM control task as well as seatbelt monitoring system. Okay, you can observe that if ignition is on in this particular LRAM control task, if the timer has expired, okay, if 10 seconds has expired, next step is check the ignition. Check if ignition is on and seat belt is off. Then what we are supposed to do, we are supposed to start the LRAM, okay, as well as we're supposed to set the event, that is LRAM start, and wait for the signaling of the LRAM time expired. Okay. So you can observe here when the LRAM starts, the signal will be given to the one more function, that is LRAM timer task. Okay, wait for the event LRAM start. We get the signal from this particular task LRAM start, that is sleep for 5 seconds. Wait for 5 seconds. After 5 seconds, LRAM timer has expired and give the information. LRAM timer has expired. Okay, so that is nothing but information to stop the timer. You'll receive it from this task, or it can be stopped because of ignition is off. From where you will get the ignition of this task, right? Concurrently, this will also be executed. If it is off, the same message will be given to this, and ignition will also turn on. Or one more condition is if the seat belt is fastened. So here we have a block which will monitor the seat belt system. Right here, continuously seat belt system will be monitored. It checks whether the seat belt is on. If it is on, then a signal will be given to this so that LRAM will be stopped. That is nothing but stop LRAM. Okay, so this is how concurrently these events will be executed. Okay, so these are the different models which are available for us during the programming. Okay, in order to represent, this is a model to represent the requirement given by the user.